Okay, class, today's lesson is on the term of a single deposit account. And at the end of the lesson, hopefully you will learn to, number one, construct exponential and logarithmic models of a scenario or situation, evaluate the logarithms, express exponential models as logarithms, demonstrate the use of the change of base formula, and then evaluate common and natural logarithms. Okay, so we've got a lot to cover, so let's go ahead and get started. Okay, so the first question is, how long should funds remain in a single deposit savings account? Okay, so in previous lessons, we've learned to identify how much an investment will be given a certain amount of starting point, interest rate, and compounding frequency. And then we also sort of did the opposite. If we knew the final investment balance given a certain interest rate and compounding frequency, we could work backwards and determine what the initial deposit amount is. However, we haven't figured out, or we haven't determined how to calculate how much time is required if both the initial deposit and the final amount is known, along with the compounding frequency and interest rate. So let's take a look at this particular example. Okay, suppose we know the following. So we know P, which is our deposit amount or starting amount of $1,000. And we know that at the end of some period, we're going to have an ending balance of $1,061.52. We also know that the interest rate is going to be 2% and the investment is going to be compounded 2 times or semi-annually. All right, so normally when we solve a problem like this, we would use this equation to solve for t, okay? So we would use this b is equal to p times this entire quantity raised to the nt power. And depending on what we're solving for, we would put in various values into this equation to get our answer, okay? Now for this particular problem, if we were to put in all the known values, okay, we would say that our ending balance is $1,061.52. Our starting amount is 1,000. Our rate is 2%, so we're going to express that as a decimal, 0.02. And then the compounding frequency is semi-annually, so that's going to be 2. And this is going to be raised to the nt power. Okay, we know the compounding frequency is 2. And so now we're going to go ahead and solve for t. Now, the question is, how do we solve for t when it is an exponential variable? All right, so this is the challenge. Okay, in order to solve for an exponential variable, we need to know another math function, which is called the logarithmic function or equation, okay? So when we're talking about solving for a particular exponential variable, we have to rewrite the equation as a logarithmic equation, okay? So here's what I mean. So if we have an equation, some value a is equal to b to the c power, and we want to solve for c, we can rewrite this as c is equal to the log base b of a, okay? Log base b of a, or log of a base b. When you see the term log, it could be read 2 different ways, and you may have heard that when I just said log of a base b. Okay, so here we have c equals to the logarithm of a with base b, which is what I just said, or you could say c equals the log base b of a. Okay, so either way is correct. So when you see this log, it's going to be log base b of a or log of a base b. All right. So a couple things that we also need to be aware of with logs, okay? These are some relationships that if you know in advance, it will help you and simplify future calculations. So for example, a log of 1 base b, if that is equal to the 0, then b to the 0 power is equal to 1. okay? Which means anything to the 0 power will always be 1, which means b could potentially be any value. The second relationship is log of b, base b, equal to 1 means b to the 1 power is equal to b, okay? So whenever you see this relationship, okay, so if you ignore this equal 1 scenario, if you see log of some value, base of the same value, you should know that that's also 1. And then lastly, if you know the log of b to the x power, base b, that is equivalent to just x, okay? Because b to the x power is also b to the x power. If you didn't quite understand that, what I would do is take every single one of these values and plug them into this equation, okay? So basically take the equation and do this conversion. Take this equation and do this conversion, and you will see each one of these equivalencies. Okay, now moving on to this problem, okay, if we were to continue that example that we just saw earlier, if we were to solve for t, okay, we would first divide both sides by 1,000, and when we do, these cancel out, okay? And dividing these two would give me 1.06152, and that would equal to 1.01 to the 2t power. Okay, so now when we have this equation, we have it in this format, a equals b to the c power. So then what we're going to do is say c is equal to the log of a base b. So we're going to say that c, okay, that's our c right here, 2t. So 2t for our c is going to equal the log of a. What is my a here? 1.06152. So log of 1.06152, base 1.01. Well, where did this come from? This is my base b, my b, and this is my b. Okay, so that's where that number comes from. And then solving for t, we would divide both sides by 2, and that would isolate t, and now t is going to be this value, which is what we had earlier, divided by 2. Okay. Okay, so now we've gotten this far. We still need to know one additional thing, okay? You can't punch this value into the calculator because in our calculator, all of our logs are base 10, okay? This is not a base 10, so we need to know how to resolve this. So let's take a look at some other things that we need to know about logs. And that other thing is called the change of base formula. And what that essentially says is that the log of a number, base b, is the same thing as the log of that same number with a different base divided by the log of b, which happened to be the base of the same base that you used in the numerator. So in our calculator, we would say that log of x base 10 divided by log of b base 10 is the same thing as log of x base b, okay? And that's essentially what I've done here. So since this a value can be any value greater than 0, we're going to let a equal 10 because that is the function that we have available in our calculator. Okay, so in this next statement, it says the logs in the fractional part of the equation are now common logs. Okay, so this part here, these are common logs. The change of base formula now looks like this. So log of x base b is essentially the log of x divided by the log of b. Okay, so whenever you have this scenario, when you have a log of some number base, some other number that's not 10, it is the same as the log of that number divided by the log of this base, okay? So now that we understand this change of base formula, we can now complete the previous problem, okay? So remember we had t is equal to log of 1.06152 base 1.01, okay? So we can convert this into this new equation or new equivalent. So this is really the log of this number divided by the log of this base here. Okay, so we'll replace this numerator with this ratio or fraction. We still have it divided by 2. Now you can punch this into the calculator and you're going to get roughly 6. It's going to be 5.999 something. Okay, and 6 divided by 2 is rounded to 3. So then the answer to the original question is that the term of the account is approximately 3 years. It'll take 3 years to reach that amount. Okay, so I know that was a lot, but let's go ahead and move forward with an example. Okay, so what we have here is Maribel and Roberto want to renovate their kitchen sometime in the future. They have deposited $16,000 into an account. Okay, so that is the starting amount, and that account compounds interest monthly at a rate of 2.4%. And the question is, how long will it take until that account reaches $20,000? Okay, so let's go ahead and start with the equation that we know, which is B is equal to P times 1 plus R over N to the NT power. Okay, so we know this from the previous lesson. And let's go ahead and just plug in the values that we know. So we know that we want to get to 20,000. And the initial deposit is 16,000. Okay, and the rate is 2.4%. So that's going to be 0.024. We're going to do this in decimal form, divided by the compounding frequency. Okay, we were told that it's compounds monthly. Okay, so monthly means 12, and that's going to be raised to the compounding frequency times t. Okay, so now we're going to divide both sides by 16,000. And then we're going to have 1.25. That's going to equal 1 plus 0.002 raised to the 12t power. Okay, and then further simplifying that, that's 1.25 is equal to 1.002 raised to the 12t power. Okay, and then if you recall, we had the following: A equal B to the C. Okay, so that is our format. And so then we know that C is going to be log of A base B. Okay, so that's the conversion that we need to know. So then our equation will become 12t is equal to the log of 1.25 base 1.002. Okay, and then solving for t, we're going to divide both sides by 12. And t is going to equal the log of 1.25 base 1.002 divided by 12. Okay, so now we're going to convert this to the following. T is going to equal the log of 1.25 divided by the log of 1.002, and that's all going to be divided by 12. Okay, now if we go ahead and punch that into the calculator, we're going to get the following. T is going to be 9.3 years. Okay, so that is our answer for that particular example. Okay, now we're going to talk about natural logs, and this is going to come in handy because when we talk about continuous compounding, we know that the equation for continuous compounding is the final balance is equal to the initial amount times e to the RT power, okay? And if we were to solve, if we were to rewrite this equation, divided both sides by p, we'd find that e to the RT power is equal to b over p. Now, here's what's interesting. We're going to use the conversion that we just learned, and we're going to say that RT is going to equal to the log base e of b over p. So what makes this interesting is that when you have a base e, okay, it actually requires a special logarithmic function called the natural logarithm, or ln. We call it, or we pronounce it as ln, okay? So we could essentially take this equation and replace log base e with natural log, okay? So if we were to replace that, then RT is going to equal to the natural log of b over p. And dividing both sides by r, we are able to isolate t, and now t is going to be equal to the natural log of b over p, all divided by r, okay? So this calculation is a little bit easier because we're using natural log. Now, there are some equivalencies similar to the logs that we need to be aware of, okay? So here are some special natural log values. So the natural log of 1 is equal to 0 because, you think about it, this is a base e, right? So this can be e to the 0 power is going to equal 1. So that's similar to the log of 1 is equal to 0. We also have the natural log of e is equal to 1, and that's because e, which is down here, raised to the 1 power is e. And then lastly, the natural log of e to the x is equal to x because e to the x is also equal to e to the x, okay? All right, so let's go ahead and take a look at a particular example and see how this works. Okay, so let's make sure we remember this equation. And because we're going to utilize this in this next example. Okay, so in example 2, Pedro deposits $8,000 into an account that compounds continuously at a rate of 3.7%, okay? So the key word here is continuously. When we talk about continuous compounding, we should automatically know that we're going to use the number e, or natural log in this case. Okay, and the question here is, how long will it take for his money to grow to $10,000? Okay, so let's go ahead and paste that equation here. Okay, and we're looking for t, so we can go ahead and plug in these values. So t is going to equal the natural log of the final balance, which is 10,000, divided by 8,000, which is the initial deposit, all divided by the interest rate in decimal form. So that's going to be 0.037. Okay, and now if we go ahead and plug that into the calculator, we get t is equal to 6.03 years. Okay, so it'll take just a little bit over 6 years for the final balance to reach $10,000, assuming that Pedro deposits $8,000 and earns a continuous compounding rate of 3.7%. Okay, hopefully that made sense. If anything was not clear, please go back to the beginning of the recording and listen to this again. Thank you.